In this video, we are looking at the question, what are the properties of rotational motion? For some of this, it will be a review of things that we've talked about already, while others will be some new concepts. The things that we've already talked about, I'm just going to kind of review and go over the demonstrations or the definitions, whereas with the new ideas, we'll actually look at some examples and talk a bit more in depth. The first thing we want to do is review a little bit. And one of the things we want to review about rotational motion is linear speed. Linear speed is the distance traveled per unit time. It is essentially how fast something is moving. Some examples of speeds would be 10 meters per second, which means we move 10 meters every second, and 50 miles per hour, which means that we have an object that moves 50 miles every hour. Now this is different than what we talked about in this section about rotational speed. Rotational speed is the number of revolutions an object makes per unit time. It is essentially how fast something is spinning. For example, we might have something spinning 10 RPSs, or rotations per second, versus something that might be spinning at 150 rotations per minute, or RPMs. When we look at records spin at either 33 1/3 RPMs, that would be for a long playing disc or an album, versus something that might be a single that spins at 45 RPMs. We call those 45s. The example that we gave earlier was something about students doing the whip. And I'll show you this again. These students doing the whip, meaning that they're staying in a straight line as they go in a circle. We see that even though they have the same rotational speed, the person on the outside has the faster linear speed or tangential speed. So those on the outside have a faster linear speed because they go a further distance in the same amount of time, but they all had the same rotational speed because they all go through the same angle in the same amount of time. Now, next thing we want to look at is something called rotational inertia. This is an object's resistance to changing its rotational motion. It is essentially saying how difficult it is to get something to spin or to get something to stop spinning if it already is. We talked about inertia before, and this is simply inertia applied to a spinning object. Some examples of things with a large rotational inertia would be the Earth. It would be very difficult to get the Earth to stop rotating. However, a marble has a small rotational inertia because it would be very easy to stop a marble from rotating if it's been rotating already. I do have an example, a demonstration, that I'd like to show you of the rotational inertia. And so we see again, this moment of inertia is how difficult it is to rotate an object. And so the blue one was a lot more difficult to rotate because of where the mass was located. The red one was easier to rotate because the mass was located closer to the man's hands. The next thing we want to talk about is the idea of torque, which we've talked about already. Torque is a twist or a turn, and it causes an object to rotate when a force is applied. Some examples of torques would be opening a door, we rotate the door, or twisting the lid on a water bottle, we are twisting that cap. Some demonstrations, again, opening a door and the location of the handle, we always want the handle to be as far from the hinges as possible to give us more leverage, because torque not only depends on force, but it depends on leverage as well. The further away the force is from the axis of rotation, the easier it is to rotate. The next thing we've already talked about, but we'd like to review, is center of gravity. The center of gravity is the point at which all mass of an object can be thought of as located. If an object rotates or spins, it always rotates around its center of gravity. For a symmetrical object like a meter stick, the center of mass or center of gravity is located at the center of the object. So for a meter stick, that is at the 50 centimeter mark. However, for something that is asymmetrical, for something that is not the same on the left as it is on the right, like a baseball bat, the center of mass or center of gravity is located towards the larger end. So for a baseball bat, the center of mass is towards the larger end of the bat. A new idea we haven't talked about yet is something called the centripetal force. This is any force that causes an object to maintain circular motion. The word centripetal itself is a Latin term which means center seeking, or towards the center. And so the direction of a centripetal force is towards the center. In fact, if you look at the word centripetal itself, the word center is practically in the name. So hopefully that'll help you remember that the direction of the centripetal force is towards the center of the object. Now this is not really a new force, it is just another force acting the part. Kind of like an actor or an actress in a play. Let's say we have a play of Hamlet, Shakespeare's Hamlet. And we have John Doe playing the part of Hamlet. Now, Hamlet is not really a new person. It is really just John Doe in disguise. And the same thing here, centripetal force is not really a new force. It's simply another force in disguise. For example, if we have a mass on a string that we swing around in a circle, so here we have somebody holding this mass on a string, and they're going to swing this object in a circle. Playing the part of the centripetal force in this case is tension. The tension is acting like the centripetal force. They are one and the same. So the centripetal force in this case is the tension. For a race car going around a track, what's preventing it from sliding, what keeps it in that circular motion, is friction. So in that situation, the friction is the centripetal force. They are one and the same. Playing the part of the centripetal force is the friction. In the case of the Earth going around the sun, what prevents the Earth from flying off into space is gravity. Playing the part of the centripetal force in this situation is the gravitational force. So there's always another force acting like the centripetal force. It is not really a new force, it's simply another force playing the part, another force in disguise. So again, in this situation with a person swinging something in a circle, we always say that the centripetal force, in this case it is the tension, we always say the direction of the centripetal force is towards the center. The string pulls the can towards the center. It prevents the can from moving in a straight line. In the case of the car moving around the circle, the centripetal force is the frictional force. Playing the part of centripetal force is the centripetal, playing the part of the centripetal force is the friction. And the friction acts towards the center of that curve. If there was no friction, the car would simply move in a straight line. It would skid forward. So if the frictional force is not great enough, the car tends to skid, and it skids tangent to the path. It skids forward in a straight line. The last thing we want to talk about is angular momentum. And we've talked about momentum before. Momentum is inertia in motion. So angular momentum is an object's rotational inertia. An object that is rotating wants to continue rotating unless acted upon by a net torque. Now angular momentum is also conserved, which means that it stays the same. So if there are no outside torques, angular momentum stays the same. We see this example with a figure skater. As a figure skater spins, he or she, in this case she, pulls her arms in, reducing her moment of inertia or her rotational inertia. Just like when we were spinning the blue and the red rods, when we bring the mass closer to the person, that is going to reduce the moment or angular rotational inertia. To compensate for that, the skater's rotational speed is going to increase, as we can see from this demonstration here. We see as she brings her arms in, she's going to spin faster because we are reducing her rotational inertia, and by compensating for that, we are increasing her angular or rotational speed. Now, another example here of angular momentum being conserved, I have a video from The Simpsons that I'd like to show you. In this case, Ralph is stuck on this garbage scow, and he needs to be rescued by the principal. So what we see is by running in one direction, the container has to spin in the other direction to compensate for it. And that's the conservation of angular momentum. The total momentum was 0 in the beginning and must stay 0 at the end, so the container must spin in the opposite direction to cancel out Principal Skinner's angular momentum in the other one, the other direction.